Good evening, everybody. I think a lot of you have spent a lot of time in classrooms. I have no authority to actually make you be quiet, so thank you. You're well trained. My name's Sebastian Lay. I'm the MBL's Chief Advancement Officer, which mainly means I take care of the housekeeping. And my first task is to ask you please to do the right thing and turn your cell phones off, or anything else. If you have pagers, weirdly, I don't know why you would, or anything else that makes noise, please silence them, turn them off, etc. Because we're in for a great talk tonight, and it's an important talk, and I think that's reflected by the attendance this evening. So. A couple of things. One major housekeeping item is that the July 12th Friday evening lecture, and I should mention we're in over 130 years of these Friday evening talks and this. So 130 years of intellectual exchange without interruption. So it's pretty impressive to be a part of that, and humbling. But July 12th, Dr. Hannah Valentine from the National Institutes of Health was going to give a talk, and unfortunately, circumstances are preventing that for her. So she's going to reschedule for next summer, and instead, we're really happy to announce that Dr. Denisa Wagner of Boston Children's Hospital and Harvard Medical School will be giving the talk on July 12th. Denisa is also a Whitman Fellow. So multiple perspectives that she'll bring to her talk. Finally, two other items. As many of you know, there's a reception after the talk tonight in the Meg's room. If you don't know where that is, just follow the crowd. And there's a Q&A immediately following the talk. If you'd like to ask a question, just raise your hands. One of two individuals will bring you a microphone. Please wait for the microphone to ask your questions. Tonight's talk is both simulcast on the web and recorded. And so just please be aware of that. That's all I have for you. My last task is to introduce Nipam Patel, who is in his first summer as the director of the Marine Biological Laboratory, but it's his 19th summer spending his time here teaching students. And actually he's teaching in 2 courses this summer, which is wonderful for the students and challenging for me. So please welcome Dr. Patel.
Thanks, Sebastian. So, Jerry's title as a distinguished scientist and his membership in the National Academy is just a small testament to the contributions that Jerry has made to science through his work in the field, in the lab, and influencing public policy in the United States. And like Jerry, I also we both share a passion for education as well. And Jerry played a critical role in the founding of the Semester in Environmental Sciences program here, which is one of our flagship education programs at the MBL. And it's made a huge difference to the lives of many, many students that have come through the MBL, and made a huge difference to the MBL itself in providing a continued source of scientists who come back to the MBL to do their work. So in recognition of this and the contribution to education and the contribution to education, the MBL will name the Jerry Melillo Directorship in Environmental Sciences. So we will raise money to endow this directorship, and its purpose is to provide support for the leadership of the Semester in Environmental Sciences program going forward, securing the program and solidifying the legacy that Jerry has left or has created here at the MBL in terms of this education and the science that goes on. So thank you very much, Jerry. So it's my pleasure now to introduce Chris Neill from the Woods Hole Research Center. So Chris, like many of us, actually has strong ties to the MBL and has worked with Jerry. And so Chris will give the introduction to Jerry. Thank you, Chris.
Well, thank you, Nipam. It's just a tremendous pleasure to stand up here and introduce tonight's speaker, Jerry Melillo. Jerry is a good friend. He's been an absolutely invaluable personal mentor to me, and he's also been a very much a leader at the MBL and someone who connects the science of the MBL out in the world. And I want to give you a couple examples of that tonight. Jerry's had an illustrious career that's included service at the National Science Foundation, presidency of the Ecological Society. I'm not supposed to be able to list all these things or I'd never get through it. The most impressive to me was leading more than 200 other scientists in putting together the latest national climate assessment. And if you've ever led 5 scientists, let alone 250, you know what a talent Jerry has for that work. And oh, by the way, he shared a Nobel Prize in 2007 for his work with the Intergovernmental Panel on Climate Change. But this is a Friday night lecture, and I really want to focus on Jerry's science and his remarkable contributions just to the way that we think about doing environmental science in the US and in the world. And I had the tremendous good fortune to witness those firsthand when I started to work as a postdoc in 1991 with Jerry on a new project that he had just started up with, of course, a grant and a new team that he was putting together to study what at that time was an emerging global problem, and that was trying to understand how deforestation was altering the Amazon. And I saw Jerry's remarkable ability to sense big questions in ecology and global change, sort of as they were, or before they were happening, and then to get to work on them before everybody else with remarkable teams of people. And I made a trip with Jerry to Rondonia in April of 1992, and we ended up working on the right question at the right time with the right group of Brazilian and US colleagues, and it really put us on the map in terms of studying deforestation, but it also, I'm very grateful, kind of launched my career. And it was a time when Brazil was losing about 1 state of Massachusetts of forest per year. And then the second trip we made was a few years later, and long before other people were working on the evolving issue with deforestation in the Amazon. We made another trip into Mato Grosso state to figure out sort of how soils and forests were responding to the intensity of agriculture that was occurring there, the intensification, not just the clearing, but then the intensification. And so I still work on that question. That launched me personally, and it still sustains a great deal of science. What I find remarkable as I think back about this was at the same time Jerry was assembling here at the MBL 2 other major teams in 2 other major research efforts. One was a team to launch an innovative soil warming experiment. I'm sure you're going to hear something about that tonight. And the other was a team to build global models in a way that would allow the work that was going on the ground to be applied to understanding the change at regional up to the planetary level. So that's what's unique about Jerry. He combines the ability to perform field experiments, to examine mechanisms of change, capture that change in models, test predictions for large regions. And he's a master at the synthesis, not only of his own work, but the work of dozens and even hundreds of other scientists. And that work is just absolutely vital, and he brings it forward into decision-making that allows us to address what I think is now the most urgent question for humanity. How is the Earth changing, and how are humans changing the climate? What will that mean? There's really no more important field of science right now for the future of humanity than what Jerry's going to talk about tonight. All of our advances, medicine, human health, and making people live longer will fade into insignificance if we can't maintain a habitable and biologically rich planet. So this combination of talents wrapped up into one absolutely remarkable man has inspired me, all of us who've worked with him at the Ecosystem Center and the MBL over the years. But I think more importantly, Jerry's career, which is still going strong despite his retirement, serves as a model about how to shape institutions to address these critical problems and how to make the entire field of environmental science creative, relevant, and impactful. Please welcome Jerry Melillo.
Chris, thank you very much for that introduction, and thank you all for being here tonight. Sebastian's comment about this being the 130th year of Friday night lectures. I realize that I've been here for 43 of those, which is about a third. But I look around the room and I realize I'm still a kid relative to some of the folks who are here. And so I honor all those who are in their 50th or maybe 60th year of lectures here at MBL. So tonight I'm going to talk to you about climate change, as Chris said, and the fundamental question is, which world are we going to choose going forward? And when you think about it, having to ask that question is quite extraordinary. And so I want to start out tonight by giving you the take-home messages. They're simple messages, and I would like you to repeat them often to your friends, to your associates, because we need everyone to take this issue seriously. The first one is that human-caused climate change is happening now, and it's disrupting the lives of people across this country and around the world. And as I was driving to Woods Hole in that heavy rainstorm tonight, I was thinking that that kind of a weather event is actually one of the prime indicators of climate change's influence on the Northeast right now, and I'll show you a little data that will back that up in a second. The second is that we know what the primary driver of this human-induced climate change is, and it's the emission of greenhouse gases from the burning of fossil fuels. It's really straightforward, and I'll talk a little later on about the fact that we have indisputable evidence with stable isotope data that confirms that the carbon dioxide that is accumulating in the atmosphere is actually coming from the burning of those fossil fuels. And then the final message is, and this is where hope lies, there's still time to do something about it, but the clock is ticking. And as we think about future generations, we need to very seriously take action on this issue. So those are the take-home messages. So if you get nothing else out of the parade of slides and so on, please try to remember those. Okay, my talk's going to have 3 parts. I'm going to talk about climate change, kind of the basics, the drivers, the key indicators, the current impacts of climate change, which we're all living through. Secondly, I'll talk a little bit about climate futures and what scientists using simulation models and scenarios think about the alternative futures and talk about possible impacts, response options, and finally, some hard climate choices. And then finally, I'd like to just talk briefly about global ecology at the MBL, which has been in activity for 4 decades at the Ecosystem Center, and it's involved laboratory work, field work all over the world, and as Chris mentioned, numerical modeling studies on biogeochemistry and global change. So that'll be the outline. Okay, I'm going to begin with a person that I revere, Roger Revelle, who is famous in the world of oceanography and climate change. He was a National Medal of Science winner in 1990. His daughter Mary is here with us tonight, and I want to give her a warm welcome. So in May of 1956, Roger Revelle was interviewed by Time magazine. Very short interview, and he was talking about one big greenhouse. This is 1956 now. And he is talking about the fact that the burning of fossil fuels is going to create a problem for our climate. And he said that in 50 years or so, this process of burning fossil fuels and pumping these greenhouse gases into the atmosphere may have a violent effect on the Earth's climate. And we're beginning to see that set of violent effects. So this was kind of the first public warning in a popular magazine, as far as I know, by Roger Revelle, who for the remainder of his life doggedly pursued this issue. And in the next year, 1957, he and an Austrian scientist named Hans Suess published a paper that basically explored this issue a little further. And the main focus of the paper, because both of them were very interested in oceanography and ocean function, was to describe how oceans were a major sink for carbon dioxide. And the question in their mind was, how long could that go on, especially in the face of accelerated use of fossil fuels? And so they set out a research agenda. They initially answered the question for the short term and said, we think that at least for a while, the oceans are going to be able to manage this extra CO2 in the atmosphere, and ultimately it will be dissolved in the ocean and taken out of the atmosphere. But their fundamental question was, how long would that last? What mechanisms would be involved in that continued ocean uptake? And then, by the way, there's another system besides the oceans, and that is the land. And the question was, what is going to be the function of land ecosystems in the global carbon cycle? Will it ultimately be a source or a sink of CO2 to the atmosphere as the climate warms? So, just to make sure we're all on the same page, the greenhouse effect basically describes the Earth's energy budget, energy coming in from the sun as light, shortwave radiation, and then being reflected back out into the atmosphere as heat, long-wave radiation. And the deal is that if you put a lot of greenhouse gases in the atmosphere, they will trap a portion of that outgoing heat and keep it close to the Earth's surface, which leads to global warming, of course. I'm very interested in history of terminology. My son is an environmental historian, and I'm always trying to look for little tidbits to send him for his classes. Apparently, the first mention of it in the context of climate change was made by a Swede, Neill, Takehome, in 1901. And the idea had been around long before that, with Fourier, the French mathematician and physicist, Arrhenius thinking about it in Sweden, Tyndall thinking about it in the UK, and so on. So the idea has been around for a long time, and fairly early it was recognized that carbon dioxide was going to be an important player. And eventually we figured out that there were other important greenhouse gases, including methane and nitrous oxide, and more recently the chlorofluorocarbons that are used in refrigeration. Today, carbon dioxide is the major driver, but the other greenhouse gases that I just mentioned are also important. So, to the first part of the talk, drivers, key indicators, and current impacts. And you can look at the little John Adams quote. There are some facts, and I'm going to try to lay those out quite explicitly. So, to world energy consumption. This is a map of world energy consumption from the early 1800s to the present by the source of energy. The units on the y-axis are exajoules, a quantity of energy that can do work. And as I note on the slide, 1 exajoule is equivalent to approximately 175 million barrels of oil. So the globe currently is consuming about 500 of those exajoules, and the United States is consuming about 100 of those 500. So we're major players in the consumption game. Another look at the same kind of information, but this time in terms of carbon that we put in the atmosphere. You can see, again, the same greenhouse gas players, gas, oil, coal, and also there is a contribution from land use change. Early on in the 19th century, that contribution was from the clearing and burning of forests in places like New England. Whoops, went ahead, I don't want to do that. Places like New England, and right now, most of the activity from land use emissions to the atmosphere is occurring, as Chris mentioned, in the tropics, including Brazil. And so currently, the combination of the greenhouse gas emissions from fossil fuel burning and land use change puts about a little over 10 billion metric tons or petagrams of carbon into the atmosphere as CO2 each year. And 90% of that is coming from fossil fuel burning, and approximately the other 10% is coming from the clearing of forests, largely for agriculture in the tropics today. So now, when the CO2 goes into the atmosphere, what happens to it? All of it doesn't stay there, thank goodness. And on the right-hand side, it is your right-hand side. Right and left are always trouble for me. It is your right-hand side as you look at it. On the right-hand side is basically a little schematic of the fates. About a quarter of that CO2 goes into the ocean. This was the issue that Roger Revelle was initially concerned about back in the 1950s. Some of it goes into land on which largely trees are growing and accumulating carbon in their biomass. And if we had been here at the turn of the 20th century, much of Woods Hole was deforested, and there were a lot of sheep roaming around, with a few scientists, I guess. Now those forests have regenerated, and they are carbon sinks. Well, as it turns out, in today's world, a significant amount of the emissions of CO2 that is going into the atmosphere is actually pulled out of the atmosphere through photosynthetic processes and the ultimate building of biomass. And so land carbon sinks are critical to the carbon balance of the globe at this time, and that's why people are concerned about preserving forest ecosystems among other land systems. And then finally, there's the residual that stays in the atmosphere, and currently it's getting close to 5 billion metric tons of carbon pumped in and staying there each year, and that's about 46% of the emissions. So let's look at the trace over history of the carbon dioxide in the atmosphere. There's a long period prior to the Industrial Revolution when the CO2 concentration of the atmosphere was relatively stable between 270 and 280 parts per million by volume. Eventually, however, with the onset of the Industrial Revolution, with a little addition from the forest clearing and so on that I was talking about in the 19th century, the CO2 levels began to rise. We have a good record of that early phase of CO2 in the atmosphere through the study of the composition of the bubbles in ice cores, dating them through time and then putting together a time trace of CO2 in the atmosphere. But more recently, we have direct measurements. And this is part of the legacy of Roger Revelle, because one of his postdoctoral students named Charles David Keeling was assigned by Roger. I think it was assigned. I don't know whether he chose it, but it was assigned to make very precise measurements of the CO2 concentration of the atmosphere on a continuous basis, year in and year out, on Mauna Loa, on the Big Island of Hawaii. There was a very long fetch of relatively clean air coming across the ocean, so you got measurements of the well-mixed atmosphere at Mauna Loa. And so starting in 1958 until his death, I think around 2000, I can't remember exactly, 2007, Roger made these measurements with tremendous precision, and it was basically the smoking gun in the global change issue. And it's turned out to be a family business because Roger's son, after Roger passed away, has taken over the family business and measures CO2 and other gases very precisely on Mauna Loa. So again, we thank Roger Revelle for his mentorship of an extraordinary scientist, David Keeling. So the direct measurements of CO2 are that famous rising curve with the squiggles, and the squiggles have to do with carbon uptake largely in the northern hemisphere of CO2 in the summer. So there's a drawdown of atmospheric CO2 during photosynthesis in the summer period in the northern hemisphere. And then for the rest of the year, it is released through decomposition. And so there's this up and down exchange of carbon dioxide, but there's this growing trend of CO2 concentration in the atmosphere. And this year, for the first time, we've reached a CO2 concentration of 415 parts per million. Remember, at the beginning of the Industrial Revolution, it was 280. And so CO2 is a relatively long-lived gas, hundreds, if not thousands of years, sitting in the atmosphere. So once it's there, it's going to be there for a long time, and whatever it does, it's going to do it for a very long time. The rise of CO2 in the atmosphere correlates quite nicely on the large time scale with elevations in CO2, but we have a lot of evidence supporting the links between CO2 concentration increases in the atmosphere and temperature rise. And just to note that the global annual average temperature has increased a little more than 1 degree, 1.2 degrees Fahrenheit for the period 1986 to 2016 relative to a reference period. And you're going to see a number of these graphs. And the reference period is usually a very long period against which you compare whether the value that you measured that year is less than the reference period or more than the reference period. And the mores relative to the reference period in the lower graph are CO2 concentrations by year. So it is continuing to go up and leading to very warm years. And the hottest year on record was 2016, so we've all lived through that. And the 4 next hottest years were in the same small time interval, so we've all lived through those. So the trajectory is not exactly what we would hope. By the way, there's a picture up there of David Keeling standing in front of his hand-blown glassware in the early days, measuring CO2 concentrations with great precision at that beautiful spot, Mauna Loa, on the western side of the Big Island of Hawaii. Whoops, sorry. Oh, wrong way here, you don't want to do that. Okay, the next slide basically says something very interesting, and that is that for several thousand, maybe 7,000 or 8,000 years before present, the Earth was actually in a slight cooling phase related to very large processes that go on geological timescales. relating to all kinds of things, including volcanic eruptions, the shape of the rotation of the Earth around the sun, the axis that the Earth has during those rotations, and so on. They cause long-term climate variability. What I'd like you to focus on is the very right-hand side of that curve, which basically is almost a thin line, a vertical line. And what it is showing is that in terms of temperature, this little thin line, which is largely the 20th and early part of the 21st century, is beginning to move us outside of long-term experience of Earth temperature over the last almost 10,000 years. Now, the Earth is warming. There's no dispute about that. I even read a short article by a very conservative congressperson from Florida who said that he did not go to Washington to argue about thermometers. So maybe the message is getting through. But nonetheless, the Earth does not warm uniformly. It's very patchy, and there are all kinds of reasons for this that I don't have time to go into. But fundamentally, if you look at this graphic, what it is saying is that the very high latitudes are warming much more rapidly than the lower latitudes. And this, in good measure, has to do with the phenomenon of ice albedo. And when the ice and snow melt in the northern part of the hemisphere, you have a black body that absorbs heat and then re-radiates it in that area and warms up the high latitudes quite rapidly. So this is what we're seeing at the global scale. And scientists who work on climate change have picked a number of indicators that they track over time relative to climate change. And this is a list with a little cartoon of some of the indicators that they measure quite often. And obviously they include temperature, heat waves, frost-free season, heavy precipitation, which we experienced a little earlier in the day, drought conditions, wildfires, Arctic sea ice, glaciers and ice sheet extent and mass, sea level rise, which we're very concerned about here, obviously, ocean acidity, marine species distribution, and more. And I just want to go through these fairly quickly. This is a graphic of temperature change in the US over the period 1986 to 2016. And you could probably pick out where you live. I don't know whether it's of good enough resolution for you to make a difference. But basically, the temperatures increased over this time period about 1.2 degrees Fahrenheit. And over the period 1901 to 1985 to 2016, it's about 1.8 degrees Fahrenheit. So it's a couple of degrees on average across the country, but no one lives in average conditions. And you can see some of the very warmest spots are the Northeast, for example, portions of the Southwest, the deep reddish colors. There's also a curious phenomenon, and that is what is going on in portions of the Southeast that are basically near neutral, not a lot of warming, and sometimes a little cooling in the long-term record. And we're still trying to figure out exactly what is going on there, but people are now thinking that it has to do with the movement of large amounts of water up from the Gulf of Mexico, leading to cloud formation that helps to cool locally. But anyway, this is the mosaic for the United States for temperature. And then there are heat waves, and this is an interesting graphic that appeared in the most recent National Climate Assessment, looking at a couple of measures of heat waves, and the size of the circles is related to one of two indices of heat waves, the frequency in the upper graph and the length of the heat wave season. in the lower graph. And the interesting thing to look at, and probably pretty intuitive, is that a lot of the large impacts of heat waves are occurring in the south, in the United States. And the length of the heat wave season is growing in the southeast part of the country as well. Another indicator for those of us who garden that people are very interested in is frost-free season. And this map is indicating that frost-free season is growing as the climate warms, and that's not a surprise. But the number of days that the frost-free season is extended between 1991 and 2012 is quite astounding. 10% in New England. In the western part of the country, much larger increases in the number of days that we have frost-free seasons. Speaking of tonight's weather, a really interesting indicator that people are becoming much more interested in since Hurricane Harvey and what is going on in the Midwest is heavy precipitation events. And there are two indices of heavy precipitation and its change over time shown on these two graphics. And basically, the dark blue portions are places where heavy precipitation has increased dramatically. 55 in the upper graph, 55% in the Northeast, 42% in the Midwest. This is not saying that there's that much more precipitation. It's just that the precipitation that there is coming in these extreme precipitation events. And that was the drive into Woods Hole for us tonight. Drought. Drought is tricky. There are lots of things that drive drought, but there are multiple climate change related drivers, including higher temperatures and greater evaporative loss from soils, less rainfall, of course, and then more rainfall falling in those extreme events, but not having time to penetrate into the soil, and so it just runs off. And this is a graphic for 2016. There is a drought monitoring network that the government has set up, and this is August, mid-August 2016, the hottest year on record, and certainly one of the hottest years in Texas. And you can see all of Texas in that dark brown color. That is the exceptional drought category, and it was truly devastating. And on this lower graphic, I just wanted to show you that this was kind of outside of experience. This graphic basically is rainfall versus temperature. And if you have very little rainfall and very high temperatures, drought is very likely. So take a look at this. This down here is high precipitation, relatively low temperatures. And as we go up this line, we go to less rainfall and higher temperatures. And look where 2011 is relative to this graphic. 2011 was even more devastating for Texas than this 2016 graphic would show. And this is really outside of experience, extraordinarily hot and extraordinarily dry. And one of the projections for the future for the Southwest is that more of these events are going to become regular. Another indicator that people are tracking, although again it's quite complicated, is the wildfires. Climate change is a factor in affecting them, but all kinds of other things affect wildfires and the areas burned, which is shown in this graphic, including heat, drought, and fuel load, that is the amount of stuff to be burned in forests and shrublands and so on. And very often it's the fuel load is being accumulated in these places because pests, which are being affected by climate change, are attacking trees, killing them, and then those dead trees are sitting in place on these sites. And so the fire story is an interesting one, but a complicated one. The other problem, of course, is that humans are moving into a lot of forested areas, and they become the source of ignition. Fire season has grown, especially in the West, by at least 3 months longer, and this is expected to continue as well. And a friend of mine who is a fire ecologist in California sent me this information not too long ago, and I just thought I'd share it with you. I had not really put it all together in my head, all of the California fires in 2018. We knew there were a lot, but look at some of the costs in terms of area burned, cost in dollars, almost $3.5 billion. Fatalities, there were more than 100 people who were killed in those fires in California. And again, as we look to the future, the prediction is that this is going to become more of a regular kind of event, at least the fires of this size, hopefully not the cost to human lives. Whoops. Okay, Arctic sea ice melt. This is one of the things that is helping to make the high latitudes warmer, because when you melt that ice out, as I said, we create black bodies that accumulate heat and then warm the surrounding area. And the trajectory is going the wrong way. That is, more and more ice is melting out during the summer, and this is a graphic of the summer ice extent at the end of the season in September. And you can see in the next graphic, the visualization of exactly how it is shrinking. But the point is that the rate of change is about 13% per year in a downward slope. Here's the picture of sea ice in 1984 at the top, sea ice in 2016 at the bottom. And if you take a close look, you can see a lot of blue area to the west, or your left of the ice mass there. This is really troublesome because it has some teleconnections to the jet stream, we think, and how storms develop well outside of the Alaska area. So this ice that melts, however, is not going to cause sea level rise because it's already discounted as it's displaced the water already being in place. But the melting of land-based ice is another story. And this is quite a famous picture now of the Muir Glacier in southern Alaska. First picture taken from the vantage point in 1941, the second one in 2004. 4 miles of retreat of this glacier over that time. This is a common phenomenon for most of the continental glaciers, including those in the Himalayas and Bolivia, where they ultimately are essential water sources for very large populations. So that's particularly concerning. And this is an estimate of the amount of ice that has been lost by glaciers worldwide since 1960. And it's an amazingly large number. The other ice that we worry about, of course, are the ice masses on Greenland and in Antarctica. And the story for both of them is quite rapid loss. The trend has been consistent and quite concerning for both Greenland and the Antarctic. There was a time when we were debating as to whether the Antarctic was accumulating or losing ice mass. It's now quite clear from very careful remote sensing monitoring that it is indeed losing ice mass. And to give you an idea of what this would translate to if all of the ice from these two places were to melt out, this table suggests that the Antarctic ice sheet would give us about 191 feet of sea level rise. You can imagine where your house is, I don't know. Maybe you live in Colorado, it's okay. Or the Greenland ice sheet, another 24 feet of sea level rise. The glaciers and ice caps play a relatively small role in this picture, but they're absolutely critical for water supply for humans, and that is an important take-home message. So, accelerating sea level rise. We also have quite good measures now across the globe of sea level rise, and it is increasing. This shows in the period 1993 to 2017, a 3.3 millimeter per year sea level rise, as opposed to an earlier time when it was well less than half of that. And if we look closer, in the last few years, there's even been further acceleration at the global scale. And just to take us, a little closer to home, here's Woods Hole, and a constant trajectory of sea level rise. And over the last 100 years, a little under a foot. Similar story actually for the Battery in New York City, a little under a foot. If we go a little further south, however, to a place like southern New Jersey, maybe Atlantic City, the rate of sea level rise there has been close to 1.4 feet over the last 100 years. So it is not uniform, and this is all relative sea rise. So it includes both the rising ocean waters and any subsidence that occurs on the land. So there's this relative sea level rise measure that is really important. Of course, one of the consequences of loading the atmosphere with CO2 is to also load the surface ocean with CO2, which ultimately creates a weak acid, carbonic acid, and that has a devastating effect on shellfish because calcium is broken down in more acidic conditions. So for shellfish, depending upon their stage of life, this can be a devastating problem. And then finally, extreme events and marine ecosystems. There are a number of examples that people talk about, the warming in the Gulf of Maine in 2012 having had major effects on American lobster and squid. And then on the West Coast, a whole cascade of effects of warming, stimulating toxic algal blooms that have affected a number of species in the Pacific Northwest. And then, of course, there's the coral bleaching events that are occurring in very warm waters. Okay, so let's talk a little bit about the summary of impacts beyond what I've just mentioned. I chaired the first 3 national climate assessments, as Chris mentioned, and helped on the last one, the 4th national climate assessment. And one of the things that these documents have proved very useful for is collecting from people around the country the impacts that they're experiencing from climate change. And in the first assessment, we held 22 listening sessions in various regions of the country, asking people what, if anything, was happening as a consequence of climate change in their place. And the stories were many, but there were a few that kept on being repeated, and I just want to share the big topics with you, and I'm sure they'll resonate with you. The first is the issue of human health. Many dimensions to this connection between climate change and human health. One of the things for us here in the Northeast is Lyme disease. And ticks are in a milder climate doing better over winter, and the animals that carry them around are also doing better, and there's been a continued rise in the incidence of Lyme disease in the Northeast. And you can see on that far left side map there, it maps the total increase in cases per 100,000 people, and we're at the very high end here in New England at 100 cases per 100,000. So when you go outside this summer and come back in, check for the black-legged tick, because that's the carrier, and its expansion is related to climate change. The other issues that people really spoke of very often were water issues: too much, too little, particularly the quality and reliability of water supply. This is a picture of Lake Mead on the Colorado River, which services a large part of the Southwest with water. And over 2 decades of drought, you can see the little bathtub ring that is growing around Lake Mead as the water has drained out of that system and not been replenished. For much of the Midwest, Great Plains, this notion of crop damage from extreme weather is a big deal. That 2011 point on that line that I showed you before, the very hot, very dry places, this is a soybean crop on a farmer's farm in 2011 in Texas during that heat wave, and you can see the cracks in the soil and the devastation to the soybean crop. And then down here in the lower right is something fairly close to home: flooded New York subways during Superstorm Sandy. And there was a storm tide of 14 feet, which breached some of the barriers. About 9 feet of this was from storm surge. So that's another important thing to keep in mind. On top of sea level rise during storms, we get this additional surge that can affect land. And this is one of the things that people are really concerned about. The list of human health effects, by the way, is quite long. And the consequences are in many ways very obvious, but they range from asthma to cardiac failure to various vector-borne diseases, including cholera, cryptosporidia, and so on. And this is a major concern of the CDC, and they've done a lot to try to educate people about how to deal with this. Okay, looking forward to the future. Very quickly, here we have a set of scenarios that scientists have developed to think about climate change in the future related to the emission of greenhouse gases, in this case, carbon emissions. And the point is that looking at those emissions and then looking at the projected temperature changes, we could, if we're not aggressive about trying to deal with climate change, move into environments that we have no clue about the consequences of. Very hot and very dangerous portions of the global environment. And the big pressure now is to see if we can follow the lower green line. This is the 2-degree trajectory that we should be on if we don't want to exceed 2 degrees Celsius relative to pre-industrial conditions. And it involves some pretty drastic reductions in the emissions of CO2 to the atmosphere over time, largely from the burning of fossil fuels. And so there's a tremendous challenge. And when you look at this set of lines, if these were our choices, it is clear which choice we would want to choose, and that is to be on this line, but it comes at cost because it does affect the amount of CO2 that we can emit from current energy use. You can talk about the dangerous paths forward if we don't have aggressive reduction in emissions, and I briefly listed them here. Heavy precipitation, floods in both coastal and inland, droughts, especially in the West, Category 3 and 5 hurricanes making landfall as being more common, and surge on rising seas, which we just talked about with the New York case. And the consequence issues are health, infrastructure, security of food and water, national security, and if I'd had time, I'd talk to you a little bit about that, because I had spent a fascinating week at the Army War College in Carlisle, Pennsylvania, with young and rising military leaders talking about the national security issues. And then finally, the challenge of threats to the biosphere, which is our life support system, all of the natural systems that we rely on for goods and services that we don't pay for but that are essential for life on Earth. Okay, so very quickly, options. We can do two things, basically. We can push mitigation, that is lowering the emissions of climate changing gases that are caused by human use of fossil fuels, and also by lowering emissions from land use. And secondly, we can adapt to the challenges that are going to happen in the short term that mitigation is not going to be able to correct immediately. So those are our two options, and we're going to need both. And the longer we delay with the mitigation, the more we're going to have to do with adaptation. And the question is, are we going to be able to do enough? The kinds of mitigation actions that we talk about are the ones that I've listed up on the top part of this graphic. In the energy sector, obviously reducing the emissions of greenhouse gases. In the forest management area, reducing deforestation and increasing reforestation or afforestation, putting forests in places where they haven't been before. And then finally, modifying agricultural practices so that they don't emit excessive amounts of greenhouse gases. And two of the gases that are controllable by, or partially controllable by agricultural modification are methane and nitrous oxide. Methane in part from animal husbandry, and nitrous oxide from the excessive use of fertilizers, especially in places like China. So there's room to address all of these, and the good news is that we have tools in hand to do that. The lower two are a bit concerning to me. The first is the scrubbing of CO2 out of the atmosphere. And right now, there are some experimental activities ongoing to perfect these technologies, but the technologies have not been developed to scale yet, and we don't know whether they're going to be effective over the long run in the time that we need them. And so this is an area of very active research, and one of the questions is, how will the energy issue play out? Will there be a large use of energy to scrub the CO2 out of the atmosphere that might put some more back in? So it's a very interesting issue. The other one is geoengineering, and basically creating cooling effects in the atmosphere, offsetting greenhouse gases coming into the Earth. And this is of great concern in part because it could have a lot of unintended consequences. Not the least of which is that it wouldn't address the ocean acidification problem because the CO2 would still be in the atmosphere and you're just trying to reduce the amount of solar radiation coming in. So that's problematic. For those of you who are really interested, I recommend a book by a man named Hal Harvey and a group called Designing Climate Solutions. I think the big issue with climate change is not the science per se and what we know, because I think we know enough to take action. It's the solutions that we pick and how the solutions are going to affect different individuals. And the point of the little graphic on the right-hand side is that in this solution set that Harvey nicely develops in this book, there's no silver bullet. You're working in a lot of different areas in the climate solution space, and you've got to work on them at the same time. In terms of adaptation, there are a variety of things that can be done in agriculture, dealing with tropical diseases, dealing with health system deficiencies now and preparing ourselves for those extreme events. There are coastal infrastructure issues, both hardening the coastline in some places and using green solutions in others. I don't know whether you've read about New York City's discussions about basically extending southern Manhattan out hundreds of feet and then creating a big buffer wall there. And the reason they can't do it right at the edge of Manhattan right now is that there's too much infrastructure buried right below the street. So if you did that, it would be, an infrastructure devastation. There are zoning codes. There are transportation upgrades. There are hazard response planning activities. All of these things and many more are doable. So a couple of things that I think we really need to be working on right away are first, some kind of a pricing a carbon tax. And I know this is anathema to a lot of people, but quite frankly, in the discussions that I've been in with economists, it's hard to think of a way that we can really promote the best use of available low and no emission technologies without some kind of tax incentive. Secondly, I think it's critically important that we develop a truly aggressive program on technological innovation for clean energy, energy efficiency, and it has to be broad-based that engages government, academia, and the private sector. And one of the critical issues is how we share information across those groups, because the private sector is very often interested in working with proprietary information. And this creates a problem in how we move that information from its place of origin out into the world, which is the sharing of technology, especially with the developing world. The next thing I think is absolutely essential is engaging diplomacy once again. We have indicated our intention of leaving in 2020, the Paris Agreement. And I think this is a big mistake because if you look at the problem, the biggest emitter of CO2 now is China, and it's going to be that for a while. And also, if you look at who owns the CO2 that is in the atmosphere now, it goes something like this: 25% from the US, 25% from the EU, then comes Russia, or then China, then Russia, and then the rest of the world. So we have a big stake in the problem in terms of responsibility, but we also have a big stake in the problem because we're no longer in sole control of the solution. We have to convince the rest of the global community to join us. So I think diplomacy is absolutely critical. And then finally, continuing to conduct climate change research, including interdisciplinary studies involving natural and social sciences. And this is going to play a big role. And I'm just going to allude to a couple of things that we've been doing at the Ecosystem Center for the last 4 decades. We've had a global ecology program that has tried to do experiments to understand key processes of natural ecosystems and how they're going to respond to climate change. In the Arctic tundra, in the tree line above the tree line in northern Sweden, as Chris mentioned, in the Brazilian Amazon, in the large rivers of Russia, including the Lena River. And this information on process activities such as decomposition and photosynthesis and so on, the basic processes that run these natural systems, is then folded into simulation models of global biogeochemistry. We're the first to develop a global model that runs at about 50 kilometers on a side across the globe and explores the what-if space of climate change for a variety of things that we care about. And we've then taken that model, and in the lower right, we folded it into an integrated assessment model that includes economists, atmospheric chemists, and physicists, our terrestrial biogeochemistry group, and again, looking at what-if futures. And we've been working with maybe 40 or 50 corporations through a collaboration with MIT that pose questions to us, and then we use these models to try to bring first order projections back to them to think with. So 2 more minutes of your time and then I'm going to stop. One is that an experiment that I've been working on for a good part of my MBL life, the last 30 years, is a soil warming experiment at the Harvard Forest in collaboration with some Harvard faculty and faculty in other places around New England. And the question is about a self-reinforcing feedback. Will global warming lead to a self-reinforcing feedback to the climate system, with warming accelerating the decay of soil organic matter, leading to the release of CO2, which would then lead to more warming? And you can imagine this cycle occurring in the ecosystems in various parts of the globe. And the question was, first of all, is there any kind of natural break in the system that would stop this self-reinforcing feedback? And if so, what is it? And secondly, what magnitudes of carbon might we lose to the atmosphere as CO2 that would fuel the greenhouse effect? And so we set up a field experiment at the Harvard Forest, where we set out large lengths of resistance cable in the soil in the plots that are labeled H. We set out some cabling in the plots that are labeled D and C, but we never turned the electricity on, so we didn't do any heating in those. And then we had controls that had nothing done to them. And over time, we measured a whole bunch of things, including the gas exchanges between the soils and the atmosphere. The plots were controlled by a fairly sophisticated system, on-off system, so that over the course of a year, we could always keep the plots approximately 5 degrees Celsius above ambient. This is what it looks like in late winter. The melt out comes early on the heated plots, and no surprise, but the microbes really kick in to action at that time. And this is basically the result in terms of respiration from the heated relative to the control plots. And just look at the lower graphic for a second. We see kind of a multimodal response over 26 years. Initially, fairly rapid loss of CO2 from the soils, then a quiescent period in the first dip, then a return to loss again from the soil systems with heating in this second peak. So initial loss, quiescent period, initial loss. And now I haven't put the new data on here, but we're into a next quiescent period. And what we're trying to understand is what is going on with the microbial community that would allow them to respond in this way. And by the way, the cumulative loss from the soil so far from warming is about 17% of the entire stock of carbon in those soils. So it is possible to elicit a fairly large response in terms of releasing carbon to the atmosphere by warming, and there doesn't appear to be an early break in the system that would stop that. And we have been working with a set of microbiologists, some of them using really interesting genomic techniques to try to understand the community reorganization of microbes that might be taking place over time, as well as some of the other biogeochemical characteristics, such as the exhaustion of relatively labile carbon pools. And the thing that fascinates me most is that several of these people were in junior high school when I started the experiment, and they are now working with us at the Harvard Forest. But we published a paper in Science in 2017, sort of documenting the first 26 years, and we're hoping we just got a new 6-year award that will allow it to go on. And it is a facility which is drawing scientists from all over the country and indeed the world. So key take-home messages from that experiment. Yes, warming is going to create a positive feedback. And the sobering thing is that if this feedback were to be widespread, you'd not be able to stop it. It's not like turning off a power plant. You don't have that choice. And so, keeping your eye on positive feedbacks in the climate system is a critical thing to do. So, we call the question, and the question is which world? And to me, the answer is quite clear. It's a world with minimal disruption to human-caused climate, or minimal disruption of the climate by human-caused action. I personally think we have a shot at this world, but we're going to have to fight like hell to make it happen. And we understand the problem, and we already have some of the tools in place that we can use to begin to solve it. Now what we need is the will, and I think that the next year or two is going to tell us what kind of will we have to address the problem, as Chris described it, as one of the most daunting problems facing society. I just want to close with some wisdom that was given to a number of us when we convened in the late 90s an Indigenous Peoples Conference on Climate Change in Albuquerque, New Mexico. And we had 50 or 60 nations represented, and the chiefs from those nations came, and they talked to us about their concerns about climate change. And a message was delivered by a fascinating person, a fellow named Orrin Lyons, who is an Onondaga Indian, and he shared with us wisdom from that tribe, and I'll let you read it for yourselves, or maybe I'll read it, because you might be too far back there to read it. Okay, it's their concern about 7 generations. And the peacemaker in this is a sage from the 14th or 15th century, not exactly sure when, speaking to the tribes, trying to bring them together as a nation. The peacemaker taught us about the 7 generations. He said, "When you sit in council for the welfare of the people, you must not think of yourself or of your family, not even your generation." He said, "Make your decisions on behalf of the 7 generations coming so that they may enjoy what you have today." So, the long view with will. Thank you very much. I guess we can take a few questions if there are any.
Just raise your hand, I'll come to you.
Are we first? Cool.
Sure.
Is it on? Yes. Hi, Doctor. We're up here vacationing from Pennsylvania this week, enjoying this corner of Massachusetts. Hometown is Carlisle. We know the Army War College well. 2 items, if we may. The emphasis that we understand is largely on CO2 mitigation. But coming from Pennsylvania, we deal with the fracking industry, and a lot of methane is being put into the atmosphere because of the fracking industry. We understand methane is a much more potent greenhouse gas than is CO2. So we'd like you to address that aspect of the economic impact. And also on the economic impact, we understand that here in Massachusetts, it's projected to cost $400 million to armor Barnstable against about a 3-foot rise in sea level over the next decade or so. And nationally, it's estimated to cost $400 billion to mitigate sea rise impact, figures that we think are abhorrently small. Do you have any figures on what you would estimate from your years of research what the economic impact of a 10, 20, 30-foot sea level rise would be on the globe?
Well,
and how it gets paid for?
Yeah. First, the easy question. Let me go to methane for a second. In the minds of a number of us, methane is indeed low-hanging fruit. And there's a lot that we can do to deal with methane losses from the current methane acquisition activities. And everything that we can do, I think we should do, because as you mentioned, methane is indeed a potent greenhouse gas, more potent than CO2 per unit of gas. And so I think that that's in a way a no-brainer. Anything we can do to reduce methane emissions to the atmosphere, absolutely critical, including some of the agricultural emissions, by the way, not just the fracking. And that, in part, means changing diets of animals, for example. In terms of the cost of armoring the coasts, not only of the United States, but the world, it is certainly daunting. We don't always have to use hard technology. We might be able to use some green technologies as well. But just the New York example alone, the estimates of multiple billions of dollars to create just one barrier buffer at the southern end of Manhattan gives you a sense of the scaling problem that we might have when we think about half of the world's population lives in major cities along the coasts of the world. It really is serious. I think the thing we have to think about, though, is that we have some time. We're not going to have 30 feet of sea level rise in this century. The estimates are probably a few feet of sea level rise. Not that that is trivial, but it gives us some time to begin to take action and also to basically look at the results of what we're doing and basically learn by doing as we go along. So adaptive learning will be an important part of the picture. But in terms of numbers, I'm sorry, I can't give you a number, but it's going to be expensive. And I guess the question is, how expensive will it be if we don't do things? And, okay.
Hello, Jerry. Thank you very much for your work and for this lecture. I wanted to ask about the contribution of agriculture and what we eat and how we grow it. And it seems there are numbers out there now that are almost 50% of the contribution to climate change and to greenhouse gases comes from agriculture. And you almost called it a low-hanging fruit in terms of methane and so on. To me, it seems it's a high-hanging fruit because it's a cultural problem. The energy production is a technological problem, and I think there is the light at the end of the tunnel that we can do this. But to change the minds of people and what they think they can eat and should eat is, I think, much more difficult.
I absolutely agree. I think that the low-hanging nature of the fruit has to do with some of the technological issues associated with leaks of methane from pipelines and so on. I mean, there's a significant amount of that methane that just goes right out into the atmosphere. And that is, for me, the low-hanging fruit. I think you're absolutely right that cultural change is really difficult. There was a Nobel Prize-winning scientist from India who worked on climate change, and he decided that he wanted to do something for the Indian government to help them reduce CO2 emissions, in their case from the burning of wood in open fires. And so he basically funded the development of very efficient stoves, and apparently they weren't a big hit because the open fires in villages were apparently a cultural component of life in that place, and it was a gathering place for people and so on. And if you were relegated to your home with this little very high-tech stove that might be very efficient, but culturally not very exciting, it wasn't as much of a success as one would have hoped. So yeah, I think cultural issues are clearly on the table, including things like amophagy, the eating of insects and insect parts. One of the ideas of growing a lot of cricket flour, or crickets for cricket flour, and making that part of people's daily diets might work in some places in the developing world where amophagy is a fairly common practice, but maybe not in Woods Hole. I don't know.
I know there are a lot more questions, but we'd like to invite you all to the Meg's room. Dr. Melillo will be there, and given the time, we want to make sure that we have enough time for our reception. So thank you again.